Okay, so what have we been doing? So we've been collecting data on Pegasi's brightness in order to generate a light curve of brightness versus rotational phase, where rotational phase is a fractional amount that the star has rotated relative to some initial starting point. So these light curves can help provide information about the surface of the star since we can't directly image Pegasi. More specifically, these light curves can help us study the star spots on Pegasi. So this is important because we can learn more about the sun and the sun's sunspots. So sunspots are cooler regions on the surface of the sun. The sun's surface has an average temperature of about 5,800 Kelvin, and star spots have an average temperature of about 4,300 Kelvin, which is why they appear so much darker. Sunspots also have an 11-year cycle, and in those 11 years, there's a variation in the number of spots. Moreover, there's a 22-year magnetic cycle where the magnetic poles alternate, so the north magnetic pole becomes the south magnetic pole and vice versa. Moreover, sunspots are regions of strong magnetic field that suppress convection, so the hot ionized gas can't rise, which is why they are so much cooler. However, sunspots are not just exclusive to the sun. But for a star to have star spots, it needs to be magnetically active, which entails that it needs to have differential rotation and convection in its outer layers. Moreover, star spots can be a lot bigger than sunspots in comparison to a star. For instance, if we take a look at the image, HD 12545 star spot encompasses a pretty large amount of its surface, and in fact, this is drawn to scale, and in fact, that star spot can engulf the sun because it's so big. So, the star that we're studying is Pegasi. It's located in the constellation Pegasus, and it's about 81 light years away. And it's a young solar analog, which means that it's a star similar to the sun, but much, much younger. And it's 75% of the sun's mass with a rotation period of about 10 hours. So we can easily measure how the brightness of Pegasi changes over time. Prior to showing the light curves, it's important to understand where the brightness variations come from. So, the brightness variations are due to star spots because they're not symmetric, or in other words, they're not all the same shape or size or perfectly circular. So if we say that this is Pegasi and this is its star spot, as a star rotates, the star spot comes into and out of our view. So when the star spot comes into our view, this corresponds to a decrease in brightness, and when the star spot comes out of our view, this corresponds to an increase in brightness, which leads to that characteristic shape. So these are our results from 2006 all the way to 2016, and it's important to note that on the y-axis this is magnitude, and magnitude is a logarithmic scale, and in astronomy, based on an old convention, larger numbers correspond to a dimmer star and smaller numbers correspond to a brighter star, so it's important to note that Pegasi is relatively dim as it's mainly situated at around 9th magnitude. So, the light curve for 2012 is different in comparison to the other years because it's a lot dimmer overall, and there's a lack of brightness variation, which suggests that the Pegasi has a polar spot. And in fact, Doppler imaging done in 2003 shows that polar spot does exist on Pegasi, and it's thought that it grows and shrinks over time. And so, with these two factors of the light curve being a lot dimmer and having a lack of amplitude variation, we can logically infer that the polar spot grew this year. So, if we say this is Pegasi and this is its polar spot, not drawn on a scale, but let's just say it's symmetrical and it's dark. As the star rotates, we're not going to see any brightness variation, so we would expect a flat line, but the star would be a lot dimmer. However, when the polar spot were to grow and shrink, this is where we would see average brightness changes over a long time period. So now that we have these light curves, we're going to employ a photometric imaging technique that we call light curve inversions to map the surface of the star based on the star spots that come into and out of view of the Earth. But we're not going to make any assumptions on the shape or the quantity of star spots. So the program's job is to find the patch intensities that best approximates the stellar surface. However, we need to be careful because it's extremely sensitive to noise. Moreover, we're always going to have noise due to measurement error. This is why it's important that we can't just choose the image that best matches the light curve, and I'll explain why. So we have a star whose surface is completely devoid of any sort of features. As the star rotates, there's not going to be any brightness variation, so we would expect a flat line ideally. However, if we were to observe such a star, our data would have a noise ripple associated with it because there's always noise due to measurement error. So now we take the same exact star, but this time the star has a bunch of star spots. As the star rotates, we would expect to see brightness variations. However, if our task would be to find the stellar surface that best represents the first light curve, the program would try to match the noise artifacts, and it would end up producing a stellar surface much like the second star, which wouldn't be our true star surface, our star's true surface. So to combat this, we introduced the objective function, E, where E is in terms of j hat, the set of patch brightnesses, I, the set of measured intensities, lambda, the smoothing parameter, and B, the bias parameter, and that's going to be equal to G, the goodness of fit, plus lambda times S, the smoothing function. And it's important to know that small values of G mean a better fit. So we want to minimize the objective function. And essentially we're going to end up with a Goldilocks scenario, where our goal is to find the smoothest surface that fits the light curve to within the amount of noise in the data but no better. And how we do this is by varying lambda. So if we would give lambda a value of 0 near 0, then G would be minimized. So, however, the surface would be covered in artifacts and it would be too rough. If we would give lambda a value that's near infinity, then S would be minimized, so we would get a surface of uniform brightness, but it would be way too smooth. So we want a value of lambda that's just right, where it does a good job of fitting the brightness variations due to the spots, but wouldn't fit the noise in the data too much. So these are results of the stellar surfaces resolved from 2006 to 2016, and the 2003 image is there to show the size of the polar spot based on Doppler imaging done that year, and the star at that point was about 0.1 magnitudes brighter than it is today, and this coupled with the fact that the brightness changes in our data has allowed us to infer that how the polar spot has changed over time, and we can see it has grown over time. Moreover, these are the pseudo-Mercator projections that we have acquired as well, and these show how the star spots have moved on the surface of LO Pegasi throughout time. So I'd like to thank the National Science Foundation, Ohio Wesleyan University, and Dr. Harmon.
Okay, thank you, Oana. Questions?
Maybe more suited to Dr. Harmon, but do you know what causes the polar spots to change size?
So, not in any great detail, but there is evidence that LO Pegasi doesn't have a cycle like the sun does in terms probably of the number of spots, because probably sunspot number, star spot number doesn't really agree very well with it. But very commonly stars have varying levels of magnetic activity, and so the overall strength of the magnetic field appears to vary with time, and so it wouldn't be surprising that the polar spot changes in size correlated with that. But that's a field of active research, understanding quasi-periodicities and stellar dynamics. So.
Juan, could you please put up the picture showing the 10-year span of polar? Yeah, that would be perfect. So I'm wondering, would you expect there to be any correlation at all between the polar spot size and any peripheral spots, like a sort of a halo type of effect, or is that a possibility at all?
Can you say that one more time?
Well, I'm just wondering if there's any possible correlation between the polar spot, the big black one at the top, and any other smaller spots that might emerge around the...
Such as this?
Yeah, such as that.
Well, according to some literature, we expect that the polar spot isn't necessarily circular, so it might have like sort of a peninsula which is what these star spots might be, but we're not exactly sure.
They might be Floridas and Texases and so forth,
Right.
shooting off of the polar spot.
Right.
Yeah.
Shooting off.
Maybe I missed it, but do you just use Li to get the size of the polar spot?
Well, yes, we gave Li different polar spot sizes, and then after we've acquired all of those sizes, we have to try to find the spot each year where the surface brightness is the same, because the star has a constant temperature; it doesn't change.
Okay. Yeah. So I never heard this before, but you said that in 2003 they did Doppler imaging and confirmed that there's a polar spot.
Yes.
Were they able? Can you get any information from that on the size of it, or does it just tell you there's a polar spot?
So they said it was roughly around 20 degrees in diameter.
Yeah, so Doppler imaging uses variations in the profiles of spectral lines that are associated with star spots on the surface. And those variations give you more information about the surface than photometry does. It's a lot harder to do Doppler imaging, but if it's available, you can get higher resolution maps as a result. And Doppler imaging is what first showed the existence of polar star spots on many stars, and LO Pegasi is one of them. So the idea is it just so happens that other researchers produced a light curve in 2003, and the Doppler image was produced from data in 2003. So we're using that as a baseline, essentially. How big was the polar spot in 2003 based on the Doppler imaging? Then we can infer from our photometry how much it changed over time after that. Because Doppler imaging is hard. There's not a lot of Doppler imaging information. Photometry is a lot easier.
So they're not doing Doppler imaging every year.
Every year, no.
They just have that
There's
2003 data.
right. There's so many targets you might want to image. So
That's cool though. That's a cool approach.
Can you go back to the statement of the model?
Oh, which one?
the one with the equation.
Oh,
Yeah. Did you say that B is subjectively selected? Is that B something an input from the user, subjectively picked?
yes, it's something Dr. Harmon contributed to this field, and in this case, we have B favor dark spots. So it's just gonna, so when the program runs, it's just gonna show the dark star spots, because star spots can also be bright.
Increasing the value of B makes the darkest patches on the surface darker compared to the rest of the surface. If you know the temperatures of the star spots compared to the rest of the surface, or at least you have a reasonable guess, then you know how dark the star spot should be. And then B is a tunable parameter that lets you make them as dark as they're supposed to be. And the program actually does a curve fitting so that it tries different values of that parameter and zeroes in on what makes the star spots as dark as they're supposed to be.
Any other questions? All right, please join me in thanking Oana again.